Welcome back to Feedback Control Systems. This is Module 6.3. We're going to discuss stability in state space. The objectives of this module is to first formulate state space stability and then provide an example of this to help reinforce the idea. So first of all, in terms of formulation of state space stability, we want to go back to our state space system here, and remember we had x dot equals ax plus bu, and then y equals cx plus du. That was our state space system, where x basically represents our state variables. Okay, so in this case, what I want to do is create what I'm going to call a times x, and that's going to be equal to lambda times x. So a and lambda, they are definitely related. So lambda basically represents the eigenvalues of the A matrix. And don't be so worried about the terminology as we go through this. We're going to show you how this gets mapped into creating a stability case for the state space. So if I look at this, if these are the eigenvalues, what we want to do is if we take the lambda x and the ax and put them on the same side, so what we're going to do is we'll move the ax term to this side, and we'll see that we have this relationship lambda x minus ax is going to be equal 0. Okay. They both have a common x, so we can factor them out. However, since x is going to be our state vector here, A is a matrix, lambda here we need to multiply by the identity matrix, and remember that the identity matrix has ones along the diagonal and zeros everywhere else. So just as a reminder for that, we're doing matrix mathematics here. Okay, and then if we want to solve for x, which we're going to call our eigenvector, again, we can't just move this lambda I minus a to the right per se, but instead we need to take the inverse of that because that's a matrix. So we need to do matrix inversion to put it on the right side. So we now have an isolation here of x. And so when we move that, notice that gets multiplied by 0 as shown here. And then we basically said, how do you calculate the inverse of a matrix? And we said it's the adjoint over the determinant, and we showed you methodologies of how to do that. So the key here is we are looking for, just like in the transfer functions that we looked at for that systems, is we always looked at sort of the denominator, the characteristic polynomial. In that case, we set that equal to 0. So in this case, when we look at this definition, in the denominator here, the determinant of lambda I minus a, set that equal to 0, solution that this is essentially the solution that isn't a null vector. Okay, I'll leave it to you to worry about the mathematics. Again, I don't want you to get wrapped around the mathematics axle here. This is sort of a formulation of it, but as engineers, we're going to get to the root of this and then show you via examples how to apply this. I'm really focusing this course on applications, less on the mathematical formulations and that knowledge. Okay, but if that is something you are interested in, please don't hesitate to reach out and we can walk through that with you. Okay, so what you'll see here is I'm going to move from eigenvalues of lambda to pole locations S through that essential mapping, if you will. So I'm left with the determinant of Si minus a, set that equal to 0, and that's going to help us relative to determining our stability. So that's going to be our key there. So let's walk right into an example. And so remember from our previous formulations that we had in state space representation, we said x dot equals ax plus bu, and then y equals cx plus du, where again, x represents our state vector, or state variables rather, and then u represents our input, y represents our output characteristic. Okay, so really what we're looking at is this first equation. You'll see on the slide I have x dot equals a. So in this case, a equals 0, 3, 1, 2, 8, 1, negative 10, negative 5, negative 2. That's our A matrix. And then our B matrix is going to be 10, 0, 0, or B vector, if you will, 10, 0, 0. Our Y equals cx. So like most of the times, there's not always a d term here, so that term is 0. So I'm left with y equals cx, as you'll see there. C is just 1, 0, 0. So that is our system that we want to look at. And for determining stability, what we want to do is formulate the Si minus A matrix here. So S times I, the identity matrix here, has 1s along the diagonal, but we're going to multiply that by S, so now we have S on the diagonal. I'm going to subtract from it the A matrix, so that just bring down my A matrix. And then I'm going to go term by term. So the first term here, I have S minus 0 is S. I have 0 minus 3, so that's going to be minus 3, and so on and so forth. Okay? Notice for the middle term here, I will have an S minus 8, so I have an S minus 8 term right there. So I can formulate that matrix on the right, which is Si minus A. And then what we want to do is take the determinant of Si minus A as shown there. Now, again, in previous modules, we showed you how to determine that determinant there. And essentially, for a 3x3 system, we can do cross-multiply in this direction, add those up, cross-multiply in this direction, add those up, and then subtract those two and formulate the determinant. So I will leave that as an exercise to see if you remember how to do that and get that equation as shown right there. So that will be an equation. And as a check, notice x dot there, since we have these 3 rows here, the A matrix is 3 by 3, we know we have 3 values of x. So 3 state variables, x1, x2, x3, which correlates with our high order polynomial there being s cubed. Okay, so that term, it's always good for a quick check of things. So given that system, if we know that and we set that equal to 0, we can essentially then use our methodology from our Routh table here. So first we can look at our S3 characteristic. S3 has a value of 1. We skip 1. We then get negative 7. Then we skip. There'd be none over there, so we could write a 0, but we don't need to. S2 now, we start with negative 6. We skip 1. We get negative 52. Well, like before, we can factor out a common multiple there. We can take 2 out. The negative 6 becomes minus 3. Negative 52 becomes minus 26. And we can use those going forward. So those are our first 2 rows based on the existing polynomial. And then we can create S1. Let's clear some ink here and just remind ourselves how that goes. Okay, so to formulate S1, how do we formulate S1? Well, we essentially need the determinant as we show here. So what we're going to take is negative 26 times 1, which will be negative 26. And then we have negative 7 times negative 3, which is positive 21. So negative 26, negative plus, and then let me write that down. Sorry about that. So if I have a 1 times 26, that's going to give me a negative 26, and then I cross-multiply. Negative 7 times negative 3 is positive 21, but because I'm going in that direction, it's going to be a negative. So if I take those two together, I'm going to get a minus 47, but then remember that it is over the term up here, which is negative 3, okay? Over negative 3, and then outside of the negative 47 was another negative sign. So you could think of these two negative signs essentially as canceling. Okay, that cancels with that, and I'm left with that original negative sign from the Routh table. So I'm left with negative 47 thirds is what you see there relative to that. The next term here is 0. So I did a cute trick here. Well, if I have negative 47 thirds and 0, if I basically normalize this, because whatever I do here, I can normalize to my 0, just make that negative 1, etc., and then finally get my last term, negative 26. So if I look at my first column here, how many sign changes do I have? I go from positive to negative, so that's 1 sign change, and then all the rest are negative. So I ended up with 1 sign change, which means I have 1 right half plane pole, 2 left half plane poles, so therefore the system will be unstable. Again, don't know where the poles are through the Routh table, only know that there's 1 in the right half plane. So looking at this system, factoring this polynomial, setting it equal to 0, I can find that the actual pole locations are shown there. And you'll see that the first pole, 7.76, is indeed in the right half plane. Okay, so that will conclude this module, looking at using the Rouse table, calculating stability from a state space system. Okay, if you have any questions on any of this material, please don't hesitate to reach out. Thank you.